Hey, so this is a video for question 2 in the Acouto optic modulator lab. You'll notice that the photodiode is on the little translator with the micrometer plunger, so I can move the photodiode side to side. And the Acouto optic modulator crystal is just on a post, nothing special about it. The laser is over here, comes out, hits this reflecting mirror, this diagonal mirror, and goes this way. And it just goes through the crystal. And those are the multiple beams. You can see that the multiple beams, they go away if I turn off the power to this radio frequency generator, which is the reason why there's this radio frequency generator can put wrinkles into this crystal, right, which multiplies the beam. But here, there's only one beam. It's just the original laser beam coming and going through undiverted, right? So on the screen over here, there's this line. It's a trace. And you can see what this trace does, or at least I hope you can see what it does. Do you see that it's telling us about whether or not light is going into the photodiode, right? I've set it up with this weird little screen, this blue screen on here that the laser is passing through. So this screen is identical to this screen here. Can you see that there's 4 slits? The slit that we are using is this third slit, this narrow one. It's not the first one, the second one, it's this third one. And there's an even more narrow fourth one. But we're going to use this one. And right now, the laser is going through that third slit and going into the photodiode, right? Which you can see is being detected there, right? So the reason that we're going to do this is because if we turn on the multiple beams, you see now we have other beams. The original beam is still going through that third slit. And this is the evidence right here. And what's really cool, if you pay attention, notice that the whole line, when I block the laser light, you're going to see this entire line, including the low spot and the high spot, all go to a low value of voltage. And I'm going to outline that value of voltage with a cursor down here, right? So so the cursor's a little bit high. Yeah, do you see that? So the whole line is dropping. But this makes sense because this high part of the trace is when the beam is not diverted by the square wave, and this low part is when the beam is diverted. It's really hard to tell, but the main beam, this really bright dot that's here, actually gets a little bit dimmer when the other beams show up. And honestly, it's because of the conservation of energy, right? So the main beam doesn't have as much energy as it normally does when it's not split, right? The other beams are evidences of energy going elsewhere, right? So this Bragg diffraction and Bragg reflection thing going on in the Acouto optic modulator crystal is a redistribution of the energy, of the way that energy is traveling through space. It's pretty neat. Anyways, another thing that I can show you is, if I don't block the laser, is if I grab onto the Acouto optic modulator crystal and I give it slight, small rotations, can you see that which beam is the brightest changes? Do you see that? And what I'm going to do is I'm going to make sure that the beam on the right side, it's the adjacent beam on the right side, is set up to be the brightest. And you can see which one I mean if I turn off all the, the diverted beams. And what I'm going to do is I'm going to rotate this until this little third slit that the laser is going through is in the place of, the second beam, right? So I'm going to move the little slit so that the opening into the photodiode is right underneath where this m equals to 1 interference beam is, right? So the initial position, if I look at the micrometer super carefully, it's really hard for you to see it, but if I read it, it says about, so 5, 6, 7, 8, and it's about, nope, not that way. That's 9. So it must have been 8 point about 7. Is that right? So it's about, yeah. So it's about, oh, it's actually basically right at 8. No, sorry, it's right at about 8.5. Let's say it's about 8.50, and that's when the signal for the main beam is very strong. So I'm gonna move back and forth around there. Can you see it shrinks away? It just gets worse. So I'm gonna set the photodiode at the location of the strongest signal. And if you look at the micrometer, the strongest signal is about 8.504. 8.504. Whoa, that's, is that right? 8.5. Sorry, no, it's 8.55. Yeah, sorry, it's 8.54. 8.54 is the initial location, so 8.54 millimeters. And now I'm going to slide the photodiode over, and we're going to watch the signal. So I need to slide it over to the right. So I'm going to turn clockwise, and you'll watch the signal go away. So the signal's gone, but I'm going to keep rotating until the signal rises again, because that slit that's in front of the photodiode opening is going to finally move underneath the m equals to 1 interference beam, or at least I hope it does. Did it happen yet? Whoa, there it is. Okay, so there it is. And that's about, its maximum value is about right there. Let's see, yeah, and if you look real close, it's really hard for you to tell in the video, but this second bright dot is above this little third slit. Impossible for me to put my finger on it, but yeah. Anyways, so yeah, the little dot's above the slit, and I have another maxed out signal. So I just need to read the location of the micrometer at this point, and at this point it's so a little bit bigger than 3. It's about 3.11 millimeters. So it moved from 8.54 millimeters to 3.11 millimeters. And so this is the separation distance between what's called the m equals to 0 fringe and the m equals to 1 fringe. And they are coming from the Acouto optic modulator crystal back here. So this is really hard. So the crystal, oh my God, is back here, right? So what we need is a distance from the face of the photodiode back to, I'm going to measure to the center of the crystal. And this is the crudest part of this lab. So roughly speaking, so this is going to be really, really uncertain, right? So that's what I'm measuring right there. So let me measure it carefully. Maybe it's I don't know if you can see. So it goes like, let's say that the middle of the crystal is around, you know, I don't know, like let's say 24.5 here, and I put the 0 of the ruler basically somewhere in the meat of the photodiode, maybe where the photodiode element is or whatever. So let's call this distance 24.5 centimeters. So what's relevant is the difference between these two distances or locations. So the difference between these two locations is this small distance here. And then I just used a ruler to measure the distance between the crystal all the way up to where the photodiode is measuring where the beams are going. 24.5 centimeters. You notice the difference in units there. And that geometry has got to do, what picture is it? It's here. So this is 0 and first order fringes. So m equals to 0, m equals to 1. This is the main beam line, and then this is the first secondary beam. And the distance d is about 24.5 centimeters, what we just measured. And this is the difference between about 8 millimeters and 3 millimeters. Right? So this distance here is called y, and this distance here is called d. I'm so sorry for being such a shaky filmer, but yeah. And what you can do with this is right here, this is called the phase velocity. It's equal to the wavelength of the ultrasonic or acoustic wave. This is the frequency of that acoustic wave. The frequency is simply the 140 megahertz. So if we have a way to figure out this capital lambda, then capital lambda times 140 megahertz is the phase velocity. So we just need a way to get lambda, right? And the way to get lambda is here. So lambda is that 24.5 centimeters divided by whatever 4-ish millimeters multiplied by the wavelength of the light in the laser. The wavelength of the laser light is about 632.8 nanometers. That's the red color, right? So can you see how you can calculate the phase velocity if you calculate capital lambda and multiply by 140 megahertz? Yeah, I'm sorry, my tablet keeps doing that. But I believe that you have all the information to do question 2 right now.